Cosine of pi over 6. Pi over 6 is adjacent over the hypotenuse, right? Cosine of pi over 3. That's going to give us adjacent over hypotenuse. It's going to give us 1/2. How about cosine of pi over 2? 0. Cosine of 2 pi over 3. Cosine in quadrant 2 is positive or negative? Negative. What do you get? It's definitely patterns, right? We doing all right? Right now we're just coming up with a list of numbers in this case. Yes. I mean, is there a way to go from the sequence to this, or from the data to actually then? In some cases, yes. It'll be a little bit easier. This one would be very, very difficult to map backwards. So, and actually, that's the whole key, is how do we map backwards? And we'll come up with strategies for that towards the end. All right. We're going to talk about continuous functions versus discrete functions. Up to now, your calculus career has only allowed you to talk about continuous functions. In fact, everything had to be continuous. The field we're about to go into, nothing is continuous. Most of you are too young to understand what I'm about to tell you. I'm 40 now. With a freaking awesome connection. Okay, so continuous versus discrete. The best way I know how to do this is, okay, so all programs, like way back in the day when programs were first written, the way it was is they were all continuous. Meaning, when you ran the program, if you entered data in wrong or you put in the wrong thing, you had to run the program all the way through to the end, quit it, and then start the program again. Okay? Nowadays, it's discrete. You can run it, and then there's a way to jump back to other places. Another example would be if we want to talk about a DVD versus a VHS. VHS would be continuous. Be kind, rewind, if you remember that phrase. Even I'm having trouble remembering it. So a VCR is going to be continuous, meaning you have to go all the way through it and then all the way back. That's why when you go to rewind something that's discrete, it doesn't rewind as smoothly as a VHS. It kind of jumps, right? So a DVD would be discrete. You can skip to a scene, right? You can index exactly what time you want to go to. You can jump to it. In many ways, discrete is going to be much more powerful for us. Okay? I used to use the example of an audio tape and a CD, but CDs are even obsolete now, but you get the idea. If we were to graph these two graphs, they would not look the same. They would have a similar shape, but they would not look very much alike. A continuous graph, we already know what this looks like, and we're going to say where x and n are bigger than or equal to 1. It's going to look something like this. Very nice and continuous, very smooth. X has the option of being any value as long as it's bigger than or equal to 1 in this case. We're limiting the domain. So x could be 1. X could be 1.1. That's okay too. X could be pi. Could be anything. As long as it's bigger than or equal to 1. This function, however, does not do that. This one's going to do this. Let me use a different color. It is only those dots. I can't connect those dots. Because n are positive integers only. Okay. We're getting there. Do we understand the difference? Here's the problem. All of our calculus that we know and love says every time, if f is continuous on this interval, then you can move on. So all of our calculus up to this point is put on hold. How do you find the area under the curve? It has no meaning, right? So we need to come up with, here's a nice example. Let's say I want to do a limit, and I get infinity over infinity. What do I use? L'Hopital. L'Hopital requires a derivative. A derivative requires that h goes to 0. Well, that means it can't go from 0 to 1 to 2 to 3 to 4. So we can't take a derivative when we're using discrete. What we can do sometimes is we can use this model as an idea of what's happening to these numbers here. So we have to be extra careful. There's going to be times that we will end up with something like this, and I'll say I want to take the derivative or the integral or something like that, and I'll say, you know what, let f of x equal 1 over x. So that's a continuous function, then I can do something that's similar to it. But we need to make the distinction. This one, calculus does not apply. Actually, there is a way to do calculus with discrete stuff. It's crazy hard. Well, you don't know any better. I understood it at one time. No, which means I never really got it. Okay, so I want to talk about convergent versus divergent.
Yeah.
This is the only day that we're going to talk about this. Everything else for the rest of the semester is going to be convergent divergent series, meaning adding up the elements of a sequence. This is the only time we're going to talk about this. And I'm going to use their definition.